Hello everybody, my name is Maria Montaño. I'm a PhD student from the University of Ottawa, and today I'm going to present part of the research I'm doing for my PhD project. This piece is about influence of the oceanic mesoscale on coastal circulation within the Bay of Plenty in New Zealand. First, I want to acknowledge my co-authors at Swanda and Joao Souza for being part of the project. Also, shout out to the organizing committee of the Ocean Science meeting for making this possible. And thank you for coming to see my presentation. So let's get started. I'll start with the outline of what to expect from this presentation. First, there's going to be a brief introduction about the Bay of Plenty, including the oceanographic background and the coastal motivation. Then I'm going to talk about the model setup. We use ROMs and the evaluation of this model, followed by some results about the regional circulation and Lagrangian pathways. Finally, some conclusions. Spoiler alert, evidence of strong seasonality and distinction between coastal and basin variability is going to be seen. I'm going to start by introducing the Bay of Plenty. The Bay of Plenty is a large embayment located in the northeast coast of New Zealand's North Island. The oceanography of this region is dominated by a general west-to-east circulation from the Tasman Sea, which is the Tasman Front, and then part of this flow attaches to the northeastern continental platform of New Zealand, following a southeastward current of subtropical water, the East Auckland Current. At the south boundary of the East Auckland Current, we have the presence of a warm core eddy, the Escape Eddy. This eddy is variable in shape, size, and strength throughout the year. Even though this area is highly relevant for a number of marine activities, there's not that many studies regarding the circulation. The first study was done in 1986, where Ridgway and Gregg stated that the East Auckland Current was the main driver of the circulation in the bay. More recent studies done in the central part of the bay have stated the relevance of wind and tide-driven circulation. The aim of this project is to get an understanding of the coastal dynamics using a continental shelf resolving regional model, looking into circulation patterns, the drivers of this, and the connectivity and dispersion throughout the coastal area. This research is part of the Moana project, which is a New Zealand-wide multidisciplinary project. One of the objectives is to deliver a range of ready-to-use products to the society. An example of this is the collaboration we are having with the Whakatahia Maori Transport. They are looking to improve the management practices of their mussel farm and planning towards expansion of it. So they are really interested on the connectivity information. To achieve the mentioned before, we developed a high-resolution hindcast model using ROMs for the Bay of Plenty. This is a one-way nested model. This means that the bounded conditions are provided by a coarser resolution model. In this case, the parent model is a 5-kilometer resolution New Zealand-wide model that we can see here. Both of these products are part of the Moana project and are available for use. For more information, you can visit the Moana project webpage. This hindcast has a duration of 25 plus years, 50 levels in the vertical, 1 kilometer horizontal resolution, and as we're looking to make our simulation as realistic as possible, high resolution bathymetry and 4 islands big enough to make an impact in the 1 kilometer grid were incorporated. The tidal forcing is included as spectral forcing at the boundaries, and atmospheric forcing is from CFSR, and this version doesn't consider river impact. After developing the model, the first step was to evaluate it. We focused on the years 2003, 2004 due to having an intensive period of observations, having a time series of satellite data, ADP data, sea level, temperature, and not only at surface, but at different depths, and CTD cast located along the bay. For this, I want to acknowledge the Moana project, Niua Bay of Plenty Regional Council, and Peter Longdale for providing these datasets. Overall, the model showed a pretty good skill for reproducing the variability. Some points that I want to emphasize and that are relevant for this talks are the wind. As we can see, here we have the model wind variability is realistic. A satellite-derived sea surface time series average over the nearshore that shows that the domain-wide seasonal cycle and wind scale variations are simulated. And last but not least, this last panel with the CTD capacity evaluation to show that the vertical structure is well represented too, showing some centimeter differences during winter due to the lack of river network, which is expected. Now, going into some results and still looking at this 2-year period, I'm going to tackle the seasonality aspect. In these plots, I'm showing the January and July average. The color map shows a sea surface temperature spatial anomaly. The black arrows are the streamlines, the gray arrows are the currents, and the dashed lines near the coast represent the 20, 65, and 200 meter ice depth. The number over the landmass represents spatial average of the sea surface temperature. Disregarding of the season, we can see the colder water near the shore indicating an upwelling favorable dynamic. If we move east into the East Cape, there's a plume of cold water also in both seasons caused by tidal mixing. This conclusion was done due to the fact that this area was not identified in the model without tides. We can also see that there's seasonality in the mesoscale feature, showing variations in the position and intensity of the warm core eddy and the East Auckland current. Neither panel shows clear nearshore intrusion of the East Auckland current, but if we look into the standard deviation of the currents, we can see that during winter, there's a stronger variability near the shore. Finally, we identified a retention zone in the Opotiki Eastern Bay region, which is the farm region. Here, the streamlines are showing a recirculation pattern, and this color map is indicating low variability in both seasons. Now, looking into the Lagrangian aspect of it, a series of particle releases were done. Clusters of particles were released every 6 hours along the 20, 65, and 200 meter azimuth. In these animations, I'm just showing the 200 meter azimuth, again for January and July, in this case of the year 2004. The colors indicate the location where they were released. And as the animation goes, we can start seeing the difference in between the 2 months. Both of them have exposure to the mesoscale dynamics in different levels, as we can see. There's more intrusion towards the East Auckland current and the East Cape eddy circulation during winter. In summer, there's a tendency of clustering and 2 dominant outflow pathways. During winter, there's signs of stronger mixing, several outflows pathways, and right now it's not that noticeable, but at the beginning there was a return western flow along the shelf break. This is for 1 month, and by the end of it, we have what seems to be a bag of M&Ms mixed with Skittles. So to get a better picture of the distribution, we looked into the PDFs for the 200 meter azimuth after 30 days for both years during January and July. The 30-day period was chosen because this is the estimated period of dispersion for the mussel larvae. In these figures, we can appreciate more aspects. During summer, the islands, especially Tuhua and Whakaari, are hotspots. Dispersion is more constrained in this band region between the shelf break and the East Auckland current location. Again, we can see clearly these 2 outflow pathways towards the southeastern region and the northwestern region. During winter, there's more dispersion throughout all the domain. There is no hotspots indicating more variability in the flow. The band region between the shelf break and the East Auckland current is wider. In general, we can see that the particles get exposed to mesoscale dynamics getting entrained in the East Cape eddy and the East Auckland current circulation. But at the same time, we can appreciate that those particles getting stranded on the coast even if they are released over the 200-meter ice bed. Talking about stranding, and due to the collaboration and interests of the Fakatohia Maori transport, we took a glimpse into where the particles were stranded along the coast. Here, we have the distribution of the particles normalized by the source receiving location. With this, I mean that the center represents self-recruitment. The left side represents the upstream transport and the right side the downstream transport. The y-axis is in logarithmic scale and represents the number of particles stranded. In this case, the exposure to the mesoscale features is represented by the reduction of amount of particles stranded while moving further from shore. Seen with the maximum peaks of the 20-meter ice bath, the 65-meter ice bath, and the 200-meter ice bath. On the right side, I'm showing the average wind rows. The colors are indicating the magnitude of the winds. We can see that in both seasons, we have upwelling favorable winds. Winds going towards the southeast are dominant, which explains the tendency of transport towards the east, which is stronger during summer. We can also see a low westward tendency. This could be a response to the few but intense downwelling favorable events. In general, the winds are more intense during winter, going in accordance with the higher mixing, variability, and dispersion patterns we have seen in previous slides. These intense winds and the strong mixing could be the reason behind the higher amount of stranded particles for the 65 and 200-meter ice bed for the winter period. Now, I know due to the results that I've just presented to you that there's a high response to winds. So the next question was, how much variability do the winds explain? For this, we took a look into the spatial structure of the correlation between the alongshore wind stress and the currents. This was done for the central area of the bay, taking 3 nearshore profiles located at the 20, 65, and 200-meter ice bed, and 3 offshore profiles located at 50, 100, and 150 kilometers from shore. The animation plan here is to show the variability going throughout the study period. Where the color map is the sea surface temperature spatial anomaly, the arrows are showing the mean currents and the lines are the sea surface height. The important part of this slide is on the right side. We have the cross correlations, and to make this easier to the eye, I'm only showing the first 60 meters and 4 profiles. The 65 and 200-meter isobath profiles for the nearshore representation, and the 50 and 150 kilometers profiles for the offshore. The red dots indicate those data points that were not statistically significant. We can see there's a separation between the coastal and basin dynamics. The 65-meter isobath presents a wind force upwelling, downwelling Ekman dynamic, having the alongshore currents positively correlated with the winds and the cross-shore currents positively correlated at surface, shifting towards a negative correlation throughout the water column. This can also be seen for the 200-meter iceberg with a lower correlation value. For the offshore profiles, we have a similar correlation value compared to the near shore for the cross-shore currents along the first 10 meters of the water column. But in general, the correlation values are really low and close to zero. Similar dynamics have been observed between the East Auckland Current and the Northeast Shelf of New Zealand in previous studies. To wrap it up, these are the take-home points. The mesoscale features are present throughout the study, but varying in location and strength. The Bay of Plenty connectivity is disrupted by this exposure to the mesoscale. There's a separation between coastal and basin dynamics. Coastal particles transport is highly dependent on wind direction and strength. Finally, Further studies are needed to identify drivers of the variability throughout the whole domain. That will be all for me. Thank you very much for joining. I want to thank the Moana Project and all the project partners. Here are my contact details and the link to the webpage if you want to check it out. Thank you and have a great day.